Good morning. In today's lecture, we will look at the concept of polarity of molecules and its many applications in organic chemistry. We already talked about polarity, but not of molecules as units. Instead, we talked about the polarity of individual bonds, and we managed to order bonds starting from non-polar, such as the CC bond in ethane, to progressively more and more polar bonds in methylamine, methanol, and fluoromethane. In this direction, the polarity of CH-CX bond increases. The quantitative measure of this polarity is the dipole moment. Dipole moment is denoted by the Greek letter mu and equals delta times D, where delta is the amount of charge on the ends of the dipole, while D is the distance between those charges. In terms of dipole moments, bonds can be ordered by their polarity. So if you have a CO bond, single bond, the dipole moment is 0.86. The units here are dBs, and this is just the unit of dipole moment. For our present discussion, it's not overly relevant how much is dBi is, since we're only looking at relative relationships. CN bond is less polar. The fluorine bond is, as expected, more polar than CO bond. CH bond is relatively non-polar. OH bond is quite polar. And then multiple bonds tend to be even more polar than the single one. So this is a CO bond, and one of the most polar bonds is C2N triple bond, which is 3.6 dBi. An important thing about the dipole moment is it's the vector quality. And when we say that something is a vector, that means that direction matters. In other words, if we have multiple dipoles, we don't just add their absolute values. We add their absolute values having in mind their orientation. For example, if we had two dipole moments, mu1 and mu2, oriented in the same direction, the total dipole moment would equal mu1 plus mu2. But if those two dipole moments were oriented in the opposite directions, then the total dipole moment would equal mu1 minus mu2, and if they're exactly equal, this could be 0. In other words, these dipole moments would cancel each other out. Now this is something that is very relevant in organic chemistry, because if we look at the molecule of carbon dioxide, we already mentioned the CO double bond is very polar, but here the two dipoles are exactly opposite to each other, and they're exactly equal in magnitude, so the overall dipole moment is 0. And this is an important fact. If we have a molecule with slightly different geometry, such as formaldehyde, here we have dipole moments which are oriented this way, and since they all kind of point out in the same directions, they add up, so the total dipole moment is about 2.3 dBi. The same thing applies in molecules like chloromethane, except that now addition involves a three-dimensional structure. But still, the dipole moments still all sort of point out in the same direction, and the overall dipole is about 1.9 dBi. This issue is important in isomerism, and this is one of the facts, one of the aspects of isomerism that is quite straightforward to understand. But if we look at the dipole moments in this isomer of dibromoethane, here the dipole moment is greater than 0, clearly at 1.9 dBi. This would be the cis isomer. In trans isomer, we'll now see that the dipole moments of bromine bonds exactly cancel each other, And the same goes for the dipole moments of carbon-hydrogen bonds. And here the dipole moment is exactly 0 in the trans isomer. So the trans isomer in this case is the less polar. Another important fact is that the lone pair counts too. Lone pairs count too. If we look at ammonia, the hydrogen-nitrogen bond itself is not overly polar. But knowing that this free electron pair contributes to the dipole makes this total dipole relatively sizable, like 1.5 divides. The same is the explanation for the large dipole moment in acetonitrile, where here we have two dipole moments which add together to give a total dipole of 3.9 divides. Water is a simple example which illustrates the same thing. It has two electron pairs. We point them as being in the same plane, and adding up these dipole moments accounts for the very sizable dipole of water, which is 1.9 divides. Now in the next topic we'll see how this presence or absence of dipole moments contributes to associations of molecules, either between themselves or with other molecules.